This is what happens when a mass attached to a spring is displaced. But how does this happen? Well, with a little physics, the mystery of the mass and the spring is unveiled. Mass on a spring demonstrates a phenomena known as oscillation, particularly simple harmonic oscillation. When something oscillates, it moves back and forth in a vertical or horizontal direction across an equilibrium point. This occurs due to the fact that oscillators have a restoring force. When you displace the mass to the right, the restoring force, in this case the force of the spring, pulls the mass back to the left in order to return it to equilibrium. But to overcome the inertia of the mass, the restoring force must pull it back with an incredible velocity to the left. So much so that the mass overshoots equilibrium, and now the restoring force must pull it back to the right. And this process continues as equilibrium is overshot again and again and again. As I previously mentioned, the mass on a spring is an example of a simple harmonic oscillator. Simple harmonic oscillators demonstrate a special relationship that was discovered by a scientist named Robert Hooke. Hooke said something in Latin which translates to as the extension, so the force, meaning that the amount that the spring is stretched, or the displacement of the mass, is negatively proportional to the restoring force. Hooke's law can be represented by the equation F spring equals negative kx, where F spring is the restoring force exerted by the spring, k is the spring constant, which varies depending on the spring, and x is the displacement of the mass on the spring. This law explains why the magnitude of maximum displacement on either side of equilibrium is the same for simple harmonic oscillators. Because the motion of a simple harmonic oscillator is cyclical or repeating, it can be represented as a wave on a position time graph, given by the function x equals a sine 2 pi over big T times little t, or x equals a cos 2 pi over big T times little t, where x is the position, a is the amplitude of the graph, or the magnitude of maximum displacement, big T is the period, or the amount of time it takes the mass to complete one cycle, and little t is time. So if the amplitude is 1 meter, the period is 5 seconds, the graph would look something like this. And if you wanted to find the position of the mass at 2 seconds, just sub the numbers into the equation and voila, you have your answer. Now it's pretty clear that the video from the beginning wasn't magic at all, just some good old physics.